I'm Andre from the High Performance Academy, and I want to welcome you to the first in our series of free tuning lessons. These lessons are going to be coming to you directly in your email inbox, and they're what I consider to be the bare minimum amount of knowledge regarding engine tuning that any automotive enthusiast should have. Now, if you're interested in getting into the industry as an EFI tuner, even better. This is going to be the perfect springboard to build your knowledge. Now, I'm going to tell you a little bit more about my background as well as the High Performance Academy in a few minutes, but for now, let's check out a dyno run with our 350Z behind us. If you've ever taken your car to a tuner and had it run on a dyno, chances are that's all you've seen of the process. You might not know what it is the tuner's doing behind that laptop keyboard, and for all you know, they could be playing solitaire or updating their Facebook status. This series of lessons is going to give you some insight into what it is professional engine tuners are doing with that laptop keyboard, but more importantly, why they're doing it. In this first lesson, we're going to look at the fuel delivery side of tuning, but before we get into that, I'll just give you a little bit of background about how I got into tuning and what High Performance Academy is. So for the last 15 years, I've been running a performance workshop based here in New Zealand, and we specialise in performance EFI tuning. Now, over that time, I've tuned literally thousands of engines, everything from world record holding drag cars to daily driven street cars, drift cars, rally cars, even the occasional private plane. And over the time I was running that workshop, I really got sick of the situation where customers would bring us cars for a tune that had been tuned elsewhere previously, and it only took one look at the map in the ECU, or perhaps a drive around the block, to realise whoever had tuned that car had no idea of the basic fundamentals behind EFI tuning. This is a really frustrating situation, and I knew that people were spending good money for inferior results or potentially even broken engines. Now, part of the problem with the industry is because there's no formal qualification path that will make you into an engine tuner. You can't go to a polytechnic or a university and take a course in engine tuning and come out the other end as an EFI tuner. And most of the EFI tuners out there in the market now kind of got into that situation because they had enough money to buy a dyno, and next thing they open the doors and they're taking money off customers and tuning cars. Now, I don't want to discredit those tuners out there in the industry who are doing a great job. There's definitely a bunch of tuners around the world who are exceptionally good at what they do, but by far the majority are doing a substandard amount of work. Now, the problem with this is it created a lack of trust out there in the industry. Customers don't trust tuners, they don't understand what they're doing, and part of this is brought about because the tuners want to make you think that tuning is some kind of mystical black art, that perhaps you have to have some God-given gift in order to be an engine tuner. Now, High Performance Academy was born a couple of years ago, and we're here to provide high quality online training courses for those people interested in learning more about EFI tuning. We're simply here to show you that there is no magic involved in tuning. It's a science, and it's a science we can teach, and it's a science you can learn. Now, enough of that, let's get into this first lesson. As I said, we're going to be talking about fuel delivery. When we really cut it back to the bare basics, there's two aspects we're looking at with tuning. One is the fuel delivery and one is the ignition tuning. And as I say, we'll start today with the fuel delivery. Now, as tuners, we need a way of talking about or discussing how much fuel we're adding to the engine. And that's usually done with the term air-fuel ratio. Now, it's simply, as its name states, the ratio between the amount of air entering the engine and the amount of fuel that we're supplying through the fuel injectors. Let's take one step backwards though and talk about what it is the engine does. A lot of people out there in the industry mistakenly think that the amount of power an engine makes is going to be very closely linked to how much fuel we give it. It's not really the case. The engine is really just a big air pump, and it's the oxygen molecules in that air that will dictate how much power the engine makes. It's our job simply to mix enough fuel with that air to allow the engine to make the power it's designed to make. So when we talk about air-fuel ratio, as I say, it's simply the ratio between the air entering the engine and the fuel we're delivering. And you might have heard a number such as 12.5 to 1 used when someone is talking about air-fuel ratio. What that number means is that for every 12.5 parts of air entering the engine, we're adding 1 part of fuel. Now that you know a little bit about air-fuel ratio, let's have a look at our AEM Infinity ECU, and we'll talk through what we've got available to look at in that ECU. Now, I know what you're thinking. Maybe you're not tuning an AEM Infinity ECU hooked up to a Nissan 350Z, but that doesn't matter. What we're going to be talking about in this lesson is the basic fundamentals of fuel delivery, and it doesn't matter if you're tuning a 4-cylinder, a 6-cylinder or an 8-cylinder engine, whether it's naturally aspirated or turbocharged, or whether you're tuning that using a Motec, a Haltech, or even reflashing the stock ECU. These principles are applicable to every engine and every software platform. Let's have a quick look through what we've got available in our Infinity ECU, and here we're on the VE or volumetric efficiency tuning page, which is where we're going to be making changes to our fuel delivery. In the middle of the page you can see here we've got our VE table, which is filled with a whole lot of numbers. Now, the numbers in this table represent the engine's volumetric efficiency. And in layman's terms, what that means is how effectively or efficiently the engine can fill its cylinders with air at any particular point in the rev and load range. So for example, when we see a value approaching 100%, like we can see up here, what that means is that at that point in the table, the engine is completely filling its cylinders with air. So in our example, we've got a 3.5 litre V6 engine. So if we have a number of 100% in this table, it means that at that particular point, the engine is displacing 3.5 litres of air per engine cycle. On this table, we have 2 axes, and on the left-hand side here, you can see we've got manifold pressure, and this represents how much load we have on the engine. On the horizontal axis, we have our engine RPM, and as you can see, as we move across to the right, the engine RPM increases. What I'll do is we'll just start the engine now, and we'll see how the ECU moves through this table as the engine's running. So right now you can see the site that the ECU is currently accessing is highlighted in purple, and you can see that at the moment we've got the engine idling. We're sitting at about 800 RPM, and you can see that we're at high vacuum here. We're sitting at around about 30 kPa. Now I've got the throttle completely closed at the moment. Now if I just give the throttle a quick blip, we can see that the ECU jumps up to the 100 kPa row, which is where we're at full throttle. So when we're running the engine at wide open throttle on the dyno, we're going to be sitting up around this 95 to 100 kPa row. That's where we're asking for maximum power. Okay, so on the right hand side here, we've also got a graphical representation of the numbers in that VE table, and this just gives us an idea of what that table looks like graphically. So once the ECU knows how much air is entering the engine, it also needs to know what size the fuel injectors are that are fitted to the engine, and that's done with another workbook or page inside the ECU. Once it knows how much air is entering the engine and what size the injectors are, it becomes relatively simple for the ECU to decide how much fuel to deliver in order to achieve our target air-fuel ratio. Now if we move over to the Lambda work page, we can see our target air-fuel ratio being displayed here. So this table has the same axes as our volumetric efficiency table. You can see we've got manifold pressure on the vertical axis, and we've got engine RPM on the horizontal axis. And the numbers inside this table are simply our target air-fuel ratios. These are the air-fuel ratios we want the engine to be running at. Again, the current site that the ECU is accessing is highlighted in purple, and you can see down here in the idle area, and also in the cruise areas, so the areas of the table that we're going to be accessing at cruise speeds, we've got a value of 14.7 to 1 in there. Now that's actually quite a special air fuel ratio for pump fuel. This is known as the stoichiometric air fuel ratio. Now I don't want to scare you off, that's a chemical term, but what it really means is that a stoichiometric air fuel ratio is where we should have theoretically perfect combustion. So all of the available fuel and air that's entering the engine are being properly combusted and burnt. That's also going to give us really good emissions, and it's going to give us good fuel economy. However, you can see that we're not targeting that same 14.7 to 1 through the entire table. As we move up, so that's as we increase the throttle opening and as we increase the load on the engine, we're asking for more power. When we're at wide open throttle, we're wanting absolute maximum power out of our engine. You can see as we do that, our air fuel ratio moves from 14.7 to 1 to 13 to 1. Now what that means is for the same amount of air, we're now adding more fuel. This is called a richer air fuel ratio or a richer mixture. Now there's two reasons why we're going to start targeting a richer air fuel ratio as we open the throttle further and increase the load on the engine. First of all, as I said, when we're at wide open throttle, we want maximum power. Now remember, it's the air, or more correctly the oxygen entering the cylinders, that's going to make that power, and we want to make sure that under that turbulent condition of wide open throttle use, that all of the available oxygen is mixing with fuel and being combusted. So to do that, we're going to add a little bit of additional fuel and run a richer target air fuel ratio. That's going to make sure that we're getting maximum power out of our engine. The other aspect to consider though is under wide open throttle, there's a lot more fuel and air being combusted in the cylinder, and that's going to result in a lot more heat inside our engine, inside our combustion chamber. So by targeting a richer air fuel ratio, that additional fuel actually helps to cool our combustion temperature, and that's going to help aid our engine reliability. It's going to mean that we're not going to risk damaging the piston, damaging the cylinder head from excessive temperature. Okay, now that we've got a bit of an overview of what's going on inside this ECU, we're going to have a look at how we can go about making changes to the fuel delivery in order to get our target running correctly. Now the process that we're going to look at with the AEM Infinity ECU is still applicable to almost all aftermarket ECUs, or even reflashing of the standard factory ECU. The user interface might look slightly different, and the exact technique we're going to be using might differ slightly, but the principles remain the same. Okay, let's move back to our volumetric efficiency workbook, and what I'm going to do is I'm going to start by highlighting a range of cells that we're going to run our engine in, and I'm just going to increase these numbers so that when we first start tuning, we're actually going to have some work to do. The engine won't be running at the correct air fuel ratio. Okay, so on the left hand side of the screen we have some numbers that we're going to be using as feedback to help us with our tuning. Here we have at the top our measured air fuel ratio. So this is the number that's currently moving, and this is measured from a wideband air fuel ratio sensor in the exhaust. Below that we have our target air fuel ratio, and that simply comes from our target air fuel ratio table that we just looked at. Okay, so we're going to get our engine running now into fourth gear on our dyno, and we'll just go through the process of adjusting the numbers in our fuel table to make sure that our air fuel ratio matches our target. Okay, so we're in fourth gear now, and what I'm going to do is run the engine in this particular cell here, which is our 40 kPa row. And what we can see is that our measured air fuel ratio is sitting at around about 12.0 to 1. So we're much richer, we've got much too much fuel going into that particular cell, and the air fuel ratio is richer than our target. Now we can fix that simply by reducing the number in that particular cell. So at the moment, in our 40 kPa site, we have a value of 74.5% volumetric efficiency, and by using the D key, I can just reduce that down, and as I reduce the value, you can see that our measured air-fuel ratio starts to move towards our target. We've gone from 12.2 to 1 now to 13.8 to 1. We're still richer than our target, so we'll continue to press the D key, and you can see that as I do that, our measured air-fuel ratio drops, and right now we're sitting pretty close to our target of 14.7 to 1. When we're making these changes, it is always important to make sure that we're operating right in the middle of the cell that we're making these changes to. So once we've tuned that particular cell and we're happy with the air-fuel ratio, I can just open the throttle slightly and we can move up to the next site, which is our 45 kPa row. And you can see as we move up to our 45 kPa row, our measured air-fuel ratio again is much richer than our target. Again, we're back down to 12.2. So we go through the same process of reducing the number by pressing the D key. And as I do that, again our measured air-fuel ratio starts to move towards our target. We're sitting at 14.4, 14.5, and now we're sitting right on our target of 14.7 to 1. So that's the process that we use to adjust the numbers in that volumetric efficiency table until the measured air-fuel ratio matches our target. And simply we go through that table using the dyno to control the engine RPM and using the throttle to control the amount of load being placed on the engine, and we keep adjusting those numbers until our entire table is tuned correctly. So that completes this lesson, and I hope that you've enjoyed it and learned something. We would love to know what you want to learn more about specifically, so feel free to let us know in the comments below. In our next lesson, we'll be looking at ignition tuning on a turbocharged Toyota 86, so you can watch out for that coming to you in your email inbox. Until next time, thanks for watching.